Well, sorry for the little delay. So, hello everyone, and welcome to the third event of our special online meetup series, Web3 Devs. Just a moment. Okay. So, before we start the event, I want to tell you a little bit about our community at Web3 Devs Underground. So, we are a community of Web3 developers that was founded on open source values by Shauli Rejwan and Roy Yosherov. Since then, we have consistently organized physical events in Israel dedicated for the Web3 developers with some of the best technical minds in the industry today. Recently, we have started a series of online events, and we're excited that you all can be a part of it. So, few words about our sponsors. MasterKey VC is an early stage venture capital that specializes in infrastructure and deep tech in the Web3 ecosystem. Team members are located around the globe on the big crypto hubs. Our team includes 16 world class cryptographers and some other technical experts, and led by Shauli Rejwan, our managing partner. So, without further ado, I'm giving the mic to our speaker today, Yogev Lidor, which is an expert coder and a dear community member. So, Yogev, the mic is yours.
Thank you, Amit. Thank you for having me. Thanks for Web3 Devs Underground and Master Key. So my name is Yogev. People tend to call me Yogi. Um, it's nice to be here. So I'm going to be going through a nice story that represents a phase in our protocol. So I'm working for a protocol called OINC. It's a protocol for mobile contribution. I will talk a little bit about it. I am coding, also leading most of the development in the protocol. And today I will share with you um, the one of the challenges that we dealt with about a year ago, um, and the way that we examined a few solutions and eventually chose a creative one, which is based on an interesting statistical mathematical algorithm. So it's not going to be like super mathematical, but I will explain a little bit about the concept that we're using to solve the problem. Um, I will start also by saying that I'm not claiming that this is going to be the only solution or the best one, but definitely a creative one and one worth knowing and understanding in order to open our minds for and have a creative mindset when solving problems. So, without further ado, I will share my screen. Um, I will also say that you're very welcome to ask questions throughout the lecture um, using the chat window. And if I see something comes up, I will gladly answer. Okay, so the title is Balancing Fairness on Chain. And we'll be talking about stake weighted selection. But maybe some of you, when you hear some kind of such an expression, you might be thinking about proof of stake. And it does relate a little bit to proof of stake, but it is important to mention that I'm not talking about the blockchain infrastructure layer. I'll be talking about the application layer. So that's a decentralized application deployed on top of an EVM blockchain. And we also not going to be talking about how to generate randomness on blockchain, but we are going to be talking about how we can do a stake-weighted randomness over a decentralized protocol. Okay, so one quick slide on OINC. OINC is a protocol for global contribution. We incentivize individuals to contribute their skills and efforts towards advancing humanity. Sounds very big and maybe philosophical, and maybe it is a little bit. And I will speak a little bit about the entities that we have in the protocol so that you have also a little bit of understanding of how things work, because I will, once demonstrating the problem, I will use the protocol language, kind of a real world sample from how we develop things in order to demonstrate the solution. So I want you to have some familiarity with the protocol. A quick one. So in this protocol, imagine that there are people that are doing things. Let's call those things good deeds. They are doing something in the real world and using some kind of valuation, a way to evaluate those deeds. We can reward for their contribution. So what we need to understand that there are deeders, people who are doing deeds, and there are evaluators who are evaluating those deeds. So far, that's it, more or less. And what you need to know is that we would like to have to match evaluator to a deed using a stake-weighted selection. So each an evaluator has some staking in the protocol. They have different amounts of staking, and their chances of being selected to evaluate a deed are proportional to the stake that they have in the protocol. So far about OINC and what I want you to understand. I will repeat those things more or less as we go forward, but the challenge that we're talking about is to select, to have a random stake-weighted selection of evaluator and to match the evaluator to a deed. Okay, we have even a slide, a bit more official. So we are balancing fairness, where high stakes means higher chances. Minimum effective stake, there's a threshold. So when we're doing this kind of like raffle, trying to match evaluator to a deed, each deed declares some kind of a minimum threshold of stake that evaluator has to have within the protocol in order to participate in this raffle for this deed. Okay, so it's not the same evaluators that are playing to be chosen for each deed. Depends on this threshold. We want to ensure transparent matching process, maintain efficiency in matching while entities increase. It's important. We don't want to scale linearly. And of course, we want to minimize the gas costs. So those are pretty straightforward requirements that we have for this challenge. And we're going to speaking more of them as we move on. So we have a deeder doing a deed, and we have a bunch of evaluators staking in our protocol. And once the deed is submitted to the system, we like to have a stake-weighted selection, a process where we randomize the evaluators and choosing one, of course, considering their stake in their system. So their chances are proportional to their stake. So there are all kinds of methods, and I'm comparing two here. Without going too deep into the implementation, I will dive into one of them as we move forward. So let's compare those two methods. The first one, on-chain dynamic state-weighted selection. On-chain dynamic stack weighted selection is actually the naive solution where we're doing all the calculations on chain. We're doing the calculation, meaning that we gonna have to iterate through the evaluators. I will elaborate a little bit more, but basically imagine that we iterate the evaluators in order to know which one actually won the deed. The second solution on the right, we call it a keeper solution. So imagine something like where you have off-chain entities, kind of like an Oracle solution. You have a few nodes that are off-chain. We should trust them. They should trust each other. And then they get the decision. They make the decision. Not going to go into how this can be implemented, but just the generic idea of having this off-chain solution where you have a few off-chain entities. Actually, they don't have to trust each other, but we have to trust them, and they can make the decision. So when it comes, I'll go quickly over the criteria. When it comes to security, so on-chain security is very high, of course, governed by the blockchain. Off-chain depends on the security of the off-chain system. So how much we trust those nodes. Complexity, consider high on-chain because you have to implement everything on-chain in a smart contract. Keeper solution, possibly simple. So smart contract is pretty simple, but possibly implementation that has to be done in each of the external nodes. Decentralization, so on-chain fully decentralized. Keeper is partially centralized, partially decentralized. Speed and efficiency, so on-chain usually considered slower. We depend on the underlying blockchain, depends on the block time constraints. Off-chain solution should be faster because faster off-chain computations are usually just faster. Gas costs are high on-chain, low off-chain, of course, and trust. So I guess on-chain trust is inherent. It's a part of the blockchain infrastructure, and a keeper solution depends again on the entities that we're using. I'm gonna dive now to the implementation, a naive implementation of the on-chain dynamic stake weighted selection. Reminding again that we have a situation where we have a deed in the system. We have a bunch of evaluators each with their stake, and we want to have a selection. We want to match a evaluator to a deed, and the selection has to be proportional to their stake in the system. And let's see a naive solution. So the steps are: compute the total effective stake. So summing up the stake of all the evaluators in the system. In this case, the first evaluator has 300 in the system, the second 100, and then 700, so total of 1100. We generate a random number after we calculate the total, and then we select a evaluator that is matching the random number. So let's imagine that we put all of them on a segment, just like in this image, and then we just throw a random ball somewhere on the segment, and then the evaluator matching the random number segment is the one that is chosen. So that's a naive solution. Why is it naive? Okay, let's see a little bit of code of how we implement this, and then let's see what are the problems that we have here. Okay, so a little bit of code. I will go through it. Quite simple. We first generate a random, basically, right, within the range of 0 to the total stakes in the system. So here it's between 0 to 1100. That's a random number. And we start to loop through the evaluators, and we get them one by one. We get the stake of each one. And we has this requirement, you remember, that evaluator has to have some minimum amount of stake in order to participate in a raffle. Each deed has its own minimum. So we are making sure that this evaluator actually can participate in the raffle. And we accumulate. We add the stake, and then we check if we already met, if we met the random number. Visually, let's see how this works. Basically, we start with 0. We have our number, a random number already. Let's say it's, 500 somewhere here. Okay, that's the random number. We start with 0. 0 plus 300. We're here, still not reached the 500. We add another 100. We reach 400, still not meeting the 500. We're adding the next one, plus 700, and we already passed the 500, so we know that it's this one. So that was a little bit of technical explanation for this solution. Just imagine that we accumulate the stakes until we meet the random number. This solution will work functional. From a functional perspective, of course, this will work, but it is problematic. So let's talk a little bit about the problems. So 2 problems with this solution. The first one, complexity scales linearly with evaluator count. So as you saw, we looped through the evaluators. So in the worst case scenario, the evaluator that matches the deed could be the last one. So that's a big O(n), where n is the number of evaluators. So we don't have any control of the amount of evaluators within the system. People can just sign up, and you can have more and more evaluators within the system, and then you scale linearly with the amount of evaluators, which of course is a bad practice on chain. It's going to be expensive, mainly expensive. Yeah. And one more pitfall is a discrepancy that may occur in a specific case where, imagine that you remember this condition where we require a evaluator to have a minimum stake in order to participate. Now, if we have a evaluator that is not qualifying and we are basically eliminating him, they do not take part in the raffle, then we can create a problem. Let's see how this works. So let's assume that the minimum amount for participation is 200. And we're starting to loop and accumulate. The first one is accumulated. Now the second one is accumulated. Actually, it isn't, because it has only 100 staked within the protocol and the minimum is 200. So we kick this one out of the raffle and we accumulate the next one, which is 700. The problem is that we are using a random that is based on all the evaluators. And therefore the random number will be somewhere between 0 to 1100, but we're going to accumulate only until 1000. If we push this one out, right, we're going to have 300 plus 700, and we will not cover the last 100. So if the random number is somewhere here, we will not be able to have a evaluator that is covering this part. So this is some kind of a discrepancy that may occur. Of course, we can loop through all evaluators and check who of the evaluators below this threshold and then loop again. But all those loops basically are just not not feasible on chain. So these are the problems with this naive on-chain solution, which is it's nice, but it's not feasible. It's just super expensive and also not even functional, as we saw in the with the second challenge. This led us to think of a hybrid approach for matching a valuator to a deed. So we saw the constraints. I will remind you the main one. We want to have a sublinear complexity. So we don't want to grow linearly with the number of valuators within our system. That's the constraint. And the title here of the hybrid approach is off-chain computation and on-chain verification. For those of you who are dealing with blockchain, I guess this is not a new concept, right? We know that on-chain things are very expensive, and we would like to use on-chain code usually for verification only if possible. So if you're familiar with, for example, ZK proofs, same concept more or less, right? You have some kind of an off-chain computation for building a proof. This can be a heavy computation, but the on-chain verification of the proof should be lightweight and easy and cheap eventually. So we didn't use ZK, but we did use a different mathematical concept, getting there. So just reading this to make sure I'm not missing anything. Validators compute the best match off-chain independently. That's the off-chain computation, the heavy lifting. Validators who believes, actually who knows, they are the winner, claim it. The claim is basically done on-chain. It's a transaction. The validator is claiming the winning, and the smart contract verifies the claim. And we're starting with the interesting part now. I'm going to start and explain the solution that we eventually implemented. Putting the protocol aside for a moment, let's dive for 2 minutes into this mathematical algorithm called rejection sampling. Rejection sampling is a statistical technique for generating observations from a distribution. Just to make sure it doesn't sound like Chinese, I'm going to explain what we see here. So if we have, let's say, a complex distribution, something that it's difficult to get observations from, rejection sampling is coming to the rescue. It helps us to generate the observation from the distribution, even though it is a complicated distribution. So for example, here we have the acceptance in blue and those who are rejected in red. And we see we have basically two functions. We have a target function and we have a proposal function. Proposal function and a target function. So proposal function is the one that where we choose something from the horizontal x. We choose and we can use any distribution, but the easiest way is to just use a uniform distribution. So let's just have a raffle and choose one of them. Let's say we chose this point, 0.4 on the horizontal x, using a random selection, a uniform random selection where they all have the same chance to be elected. We chose one, and we have a second phase, another raffle, where we integrate the stake-weighted selection. So we do another raffle on the vertical x, and here we are randomizing between 0 to the maximum. Okay, so for example, if the result is somewhere up until here for 0.4, we are accepted, else we are rejected. It's going to be more clear within a minute or two, I promise you. But this is what's important here is that we have two phases. First phase, uniform selection from the horizontal X. Second phase, another raffle, another selection, this time stake weighted selection. So we choose something here, okay, and for example, 0.4 has a higher chance of winning compared to 0.6, right? Because here, if you go up, there's so much more red. And here, if you go up, there's a lot of blue. Yeah. So the proposal function is the first one, the first step for generate initial samples from a distribution that has a known probability density. In our case, it's a uniform distribution. This is choosing someone between 0 to 1 in this case. I will connect it to the protocol in a second and it will be more clear. The target function is the vertical X, where we accept or reject based on probability density function. In our case, it's a stake weighted distribution. So the steps for rejection sampling. You generate a random sample from the domain of interest. You calculate the probability density function at this point. You accept or reject based on the criteria. Let's see how this works. Okay, so a different graph, but more or less the same also. Imagine that here we have the IDs of the evaluators. That's evaluator number 1, evaluator number 2, number 3, and so on until 11. That's what we have in our sample. And those are the stakes that they have in the system. So evaluator number 1, for example, has something like, close to 500 within the system. Evaluator number 2 has around 700. And so on. So acceptance criteria in blue, rejection in red, and let's see how we apply rejection sampling here. So phase 1, we're gonna randomize here evaluator between 1 to 11 using a uniform distribution so that they all have the same chances of winning, regardless of the stake they have in the system. This might sound a little bit confusing, right? Because it's not very intuitive, because you want to apply the stake weighted concept, but only in the second phase is where we apply this concept. You can, by the way, read or get more information about it by just Googling it or whatever, rejection sampling. So I'm not going to be proving this concept here. It's a well-known mathematical algorithm, statistical one, but it's working. So phase 1, we choose evaluator. Let's say that we chose number 7, just randomly, right? And then we have the second phase, where we do another randomization, this time between 0 to the top max stake within the system. This will be, let's say, 800. And then you can start and sense the stake weighted selection, right? Because number 7 has, let's say, 350 stake in the system. And the random number will be anywhere between 0 to 800, right? So number 7 has some chances of win, but for example, number 3 has much higher chances if they get chosen in the first randomization, in the first phase. So that's the what I wanted to explain here is the rejection sampling, the concept of rejection sampling, and how we connect this to our protocol in the end to the process of selecting or matching a evaluator to a deed using a stake weighted selection, so that each of them has a chances of being selected, and the chances are proportional to their stake in their system. So that's how we use rejection sampling to implement this concept. And I'm going back to the title of off-chain computation and on-chain verification, and let's see how this works. So off-chain, each evaluator can execute the computation for all of the evaluators, basically for themselves and for everybody, to see if they are selected or not. What's the problem or challenge here? That if each evaluator runs it, okay, I'll talk about it in a minute. So each of them is running the algorithm for their ID, right? And they are checking if they won or they didn't win. But also they will be running this for everybody else. It's not enough that they run it only for themselves. The on-chain verification will run it for a specific validator that is claiming that they won. So off-chain, okay, they do some kind of an iterative process. I will dive into it within the next slide, so no worries if you don't have a clear understanding of it for the moment. Off-chain, each validator is doing some kind of a iterative process, big O of n, going through all the basically all the validators, checking if they won. And on-chain verification, the smart contract is doing big O of 1, basically can verify that the validator that claims that they won actually won the raffle. Let's see how this works and also the challenges. Off-chain implementation. Okay, so we have some kind of an iteration iterator. Okay, let's assume it starts from 0, just goes up, increasing by 1. We have also imagine that we have an array of evaluators holding all of them, and we want to choose evaluator, and then that's the first phase, right? We choose one. That's a horizontal X, the first phase of the rejection sampling, and then the second phase, we're doing the stake weighted, so we're doing another raffle in the vertical X. So let's see how we do the first one. We're using a hash function. If it's on chain, it's going to be SHA-3. So it's closely uniform distribution. We can assume it's uniform. A good one has a very close to uniform distribution, which is why we're using a hash function. Because for the first raffle, for the first randomization, we want to have a uniform distribution so that all of them has an equal chance of winning. So we're putting the random number in. So for each deed, we have a single random number that we're using. We're putting in the iteration, which is just a number that is increasing with every round of the loop. And we normalize it to the validator's count to make sure that we have a valid candidate ID. So that's how we get the candidate ID. We get them from the validator's array. And this validator basically is a result of the first step of the rejection sampling algorithm, right? So we first choose 1 validators from all of them between 1 and 11 here. That's the first phase. So we chose evaluator. Before we continue, we like to see that the stake that this evaluator has within the system is meeting the condition of the deed of a minimum stake. If it doesn't, we move on. So we increase the iteration, and then we expect here a different candidate. Okay, so we expect let's say that the minimum is 300, somewhere here, or 400, I don't know, let's say 400. And then number 7 came back from the first phase, but it has less than 400. So we move on, we increase the iteration, and then we move on still with the first phase, but we eliminate the one that doesn't meet the minimum required stake. After the first phase, we're moving to the second phase. So we're using again a hash function. We have the random, the iteration, and the deed. So we normalize it to max stake. So this time we are randomizing a number between 0 to max stake, right? This is the second phase. And what do we do with this number? We want to see that this number, or that the effective stake of the evaluator is greater or equal to the number that we chose. So let me show you on the graph. If we chose in the first step number 4, and then in the second step we have 400, then number 4 is accepted. Okay, but if we have 800, number 4 is rejected. So in the second phase, we randomize something between 0 to 800. So yeah, again, first phase is here. We're randomizing an evaluator. Second phase, we're randomizing a stake. Yeah, and then we see if it meets the condition. So 2 and 3 are basically applying the stake-weighted selection. That's the off-chain implementation. Why is it off-chain? Why is it heavy? Because we have a while loop, and potentially we're going to be iterating even more than the number of evaluators, because we're using some kind of a hash function here. And then we're normalizing here. So potentially, easily, we're going to have the same candidate ID here multiple times. It's not efficient. Nothing we want to have on-chain. Okay, so I explained a little bit about the iteration. Let's see why we're using it. Basically, it helps us to use a single random number, right? Because the iteration is changing, iteration is increasing. The hash function includes the random any iteration, as we can use the same random number, different iteration, and still continue the process. It saves us time. We don't need to regenerate random numbers. And also we preserve the weight constraints in the second phase. We're using the iteration here. Since we're normalizing to max stake, we still keep the weight condition. Again, it helps us to use a single random for this whole process. Last technical part. We're closing close to the end. So the on-chain implementation, we saw that the evaluators are running this one on their local machines or wherever off-chain. And once evaluator is winning, they can claim that they won. And they're telling the smart contract, listen, that's my address, and I won with this iteration. What could be the potential problem? That there could be multiple winners with different iteration. We choose the one that has the lowest iteration. Okay, so since everything is transparent, the random number, everybody knows the random. Everybody knows who are the evaluators within the system. So basically, they are running everything off chain, and you can't really cheat because everybody knows who is the validator that has won with the lowest iteration. But still, the smart contract verifies it. We'll go over it within a second. But just imagine that if I'm claiming that I won with an iteration of 4, let's say, but there's another validator who won with a lower iteration, then if they claim that they won after I claimed, the contract will know it and will be able to punish me for trying to cheat. Just saying this. Okay. It's I have to say it's a little bit challenging doing this online. It's hard to feel you, but I hope that you're still with me and that it's clear. So with this function, evaluator can basically, it's not the claim function, but the claim function is calling this one. An evaluator can claim or say that they won. Let's go over it for a moment. We're going to have 2 slides. Okay, first slide is showing those 2 parts and then the other 2 parts. So let's see what we have here. So the smart contract should verify the selection, right? Let's see what the smart contract is doing. Getting the index of the selected evaluator. How do we do this? We have the random number. Okay, so it's the same random number that was used by the off-chain calculation, of course, and the iteration that was given by the evaluator. If I'm gonna go to the off-chain implementation, we see that the candidate ID is chosen using a hash on the random and the iteration. So the contract is doing just the same thing, running Kazakh 256. It's the same, it's a hash function of the random and the iteration, and normalizing to evaluator's count, getting the index of the evaluator. This is the first step, right, of the rejection sampling algorithm. We choose first, using a uniform distribution, we choose the evaluator. I'm skipping for a second. We're going to be going over this one within the next slide. And then the second phase here is the stake weighted. What do we do in a stake weighted? We are basically, it's the same thing that we did here, right? We're getting a hash of the random iteration and did ID. So it's the same here. It's a hash of the random iteration and did ID, the exact same thing. And then, of course, we compare it. So it's basically the same thing that the client did, that each evaluator ran, the smart contract is running. Let's see the other 2 parts. So after selecting the evaluator, I'm checking that the evaluator that was selected is actually the claiming one, the one that called this function claiming that they won. So this is the first step. So imagine that validator number 6 is claiming that they won. So I'm running on-chain the raffle for this part. Okay, for this X, this is the first phase we said. And I'm checking if it is number 6. If it isn't, then I'm basically reverting. Okay, if it's not, then revert, not validator. And then after running the raffle, the second phase, I'm checking, just like the client did, if the effective stake is within the range. And then if it isn't, then I'm reverting. It's not the evaluator. Notice that when claiming, evaluator is providing an iteration. Okay, a specific iteration. If another one is claiming with a lower iteration than the previous one, basically gets slashed. They're punished. The smart contract knows because once a evaluator is selected, I'm saving the iteration, and then if another one is claiming that they won with the lower one, I can punish the previous one. They all have stake within the system, so it's easy to do this. So just a few, I guess, final thoughts on this one. So we transitioned from a naive on-chain implementation to a sophisticated hybrid model, right? We started with this on-chain solution of accumulating big O of n, going over all validators, something that is not sustainable on-chain. And we shift to a hybrid solution where we do the off-chain, the heavy lifting computation off-chain and on-chain verification. We used a statistical algorithm called rejection sampling that helps us to offload everything, all the heavy lifting, to the validators, and staying with a lightweight and a very, very, let's say, gas effective code on chain. And using this algorithm and this implementation, we met our initial requirements. Right, we had a fair and transparent and effective matching process. Everybody could see everything, and also the level of complexity, on-chain complexity, was very low. We don't scale linearly with the number of validators. And this is a very, as far as I think, it's a very creative solution for such an implementation. And it was a little, I guess I was skeptical at the beginning, getting to know this concept from a friend, the concept of rejection sampling. I was a little bit skeptical about the possibility to implement this on chain, but eventually with some creative minds together, we managed to do this, and I'm glad we did. That's about it from my end. So I'm gonna go back now here. I'm stopping the sharing, and I'm gonna go over some questions. And let's see what I can. What do we have here? Okay. Alon was asking, how is the randomness achieved on chain? So we're using pre-random, basically, but also not going too deep. We're not using the last pre-random. So for each pre-random is being used for future transactions, so that there's no chance for somebody when they submit a deed or for evaluator, whenever they have no chance of knowing or predicting the random that is being used. So that's what we're using. This was also, it's a different discussion, of course, about what to do, but it was good enough for our purpose to use the pre-random. Also, I didn't mention here, but we did look into a verifiable delay function, VDF, something that I think in Ethereum has maybe in the last year they already implemented or integrated into the POS. So that's about how we achieve the randomness. Pre-random has some pitfalls as well. Not going to go into this now, but yeah. Isn't there a potential for stake because we are computing off-chain based on specific point in time, which can be different from the... Yes, okay. So the question is, we're computing off-chain in a specific point in time, and there's a challenge for the smart contract to validate because it needs to have the exact same let's say, freeze or some kind of a picture of the data. That's the random number, the iteration, and the number of validators and their stake at this point in time. It has to use the same data. It's a good question. It was a challenge. And yeah, the smart contract is kind of like saving a snapshot um, of the data that needs to be saved. This is also debatable whether this is makes things how efficient things are, but we have all kinds of workarounds there that helps the smart contract to keep this thing quite small and doesn't take too much storage or too much gas. But yes, generally speaking, the smart contract has to have access. Also, the clients, the off-chain, they all need to have the same data, the exact same data, and it has to be data that is on-chain as the single source of truth. And for each deed in a specific point in time where you make the raffle and you match the value to a deed, you need to have some kind of a snapshot of all the data that is required for the rejection sampling or stake weighted process, stake weighted selection. Yeah, that's a good question. I guess this is more or less it. I'm happy that I'm at the time constraint, more or less. If people have more questions within the chat, feel free. Else, I will just say thank you, everybody, and feel free to reach out over LinkedIn or however. Yeah, thank you, Amit. You have the stage.
So,
I can't hear you.
yeah, okay.
Yeah.
Anyways, if any of you wants to jump in and ask some questions, we will open the mics, and you will have a few minutes to try and ask Yogev anything you want before we finish. And yeah, I want to thank you, Yogev. Thank you for the lecture. It was fascinating, at least for me. And yeah, let's wait a few minutes to see if anyone else wants to ask anything.
Sure. Yeah, see that. Okay, one person is writing. I don't know if you want to chat or you want to talk. Mics are open, Amit.
Yeah, now everyone can just open their mics on their own, and then feel free to just open your mic if you want, or anyone else who wants to jump in.
Hi. At the beginning of the lecture, you mentioned that it's different from proof of stake on Ethereum. Could you just explain a little bit more about why or how is it different?
Um, I think mainly because POS on Ethereum is not done on chain. Um, it's the infrastructure layer of the blockchain. It's not on chain, right? So the validators are not running on chain; they are running nodes, and they need to just run the protocol, but they don't have um, constraints of on-chain system. So they don't have to save gas, and mainly, they don't have to do something like that. Also, one more thing, we don't use commit reveal because of the advantage that may, may happen. The advantage of the last participant if they don't if you're familiar with commit reveal, then you know that if the last participant is not submitting their random number, then they can bias the result. This is, I think, one of the reasons Ethereum applied verifiable delay functions. But again, those are, I mean, concepts. So you can run off chain or on chain, and as POS is a mechanism for stake weighted selection, but they don't have constraints of running on chain. So their challenge is how to have a selection that is not biased, basically, or probably there are more strict way to you know to um, uh, as from a mathematical perspective to put it, there are like more strict ways, but basically what's important there is that you don't bias, but they don't have any constraint when it comes to complexity or gas. Yeah, we are running on chain, so it's a little bit different.
I thank you. And the follow-up question, do you feel like the security aspect of that, as you mentioned that the lecture is sufficient?
Mm, yes, the short answer is yes. Um, so when it comes to the mathematical aspect, the algorithm is bulletproof. It's statistical, of course, but it's good enough for us to work on a statistical method. Um, and besides that, yeah, the verification is pretty straightforward, and it worked smoothly. I was very happy with the outcome, and also felt very safe. There was it may sound a little bit complicated when you explain it the first time, but generally speaking, the concept of off-chain computation, on-chain verification, there's nothing new about it. If the algorithm works, then this concept is bulletproof. It's working well. Yeah.
All right, thank you very much.
Thank you for the questions.
Hey, Yogev, if I can ask, can you hear me?
Yes.
Yes. First of all, thanks a lot for the lecture. Super interesting. A question like maybe more generic. You have like a Dune dashboard of like how did you measure like the implementations that you had in the protocol and if you maybe like give us a bit of a like how did you know okay this part maybe not working like how can you be like I guess your KPI is like the fairness kind of if like the
Yeah.
Ds are like split it across the stake evenly. So did you have like KPIs or like how did you manage it? You said you started from one mechanism. I'm sure you had your versions in the way. So like if you can give us details and if you have like a Dune dashboard, that would be very nice to see.
I don't, unfortunately. I don't know if my answer is going to be satisfying here. So uh, when it comes to off-chain, basically I would. We haven't done it yet, but basically I would just run. You want to run big numbers, some kind of a script that is running, and just basically see the statistics to see that your code is meeting the expected statistics or matching, let's say, um, the proportions of the stakes when you run with big numbers. You need to have some kind of threshold because it's a statistical model, and I guess there are some kind of measurement or threshold for um, for such algorithms. Unfortunately, I don't have something to pinpoint something specific, but the plan was to run big numbers for the off-chain code and to see that we are close to the distribution, to the real distribution of the stakes. And when it comes to on-chain, you just have to sample a few of them and to see that it works, because this is a very straightforward piece of code. It's a small piece of code and straightforward that actually just verifies you need to see that the hash functions are matching. That if you hash something off chain, you use the same hash function on chain, you get the same results. So nothing too complicated there. But unfortunately, would be much nicer if I had some kind of a dashboard that shows those tests. But I don't have any, and we still have to do it. And honestly, it was a year ago when we're not sure that we're going to be using this method anymore. Things have changed. But I still think this method is very creative and interesting, and something, just as a concept to understand that you can take some kind of a mathematical algorithm or concept and just put them on chain or some kind of in a hybrid solution and use it, and it works. So I think that was my main goal here, even though, so I'm not sure we're going to be using this specific solution in production eventually.
Cool, thanks.
How did I get into the field? I started my own thing in 2018. Actually, I had a company called SafeBlocks. I met a guy called Ron who was into the blockchain industry. He had a bunch of ideas. I came from the cybersecurity industry back then. He came from blockchain background, and we ended up coming up with an idea for developing a decentralized firewall. We did it. Long story short, it was it was a great product, but it was way too early for such a product, so it didn't work out. But I fell in love with with this, let's say, field, and the rest is history. Yeah. What do you like, hate most in your work? So I like to, I like to solve problems. Mainly, I like when problems get solved. It's very nice. What I hate to test. Don't tell anyone, but I really hate to test things. Yeah.
Awesome. And one last personal questions I want to ask is if you have any tip or trick that you found out this year that you want to share with the community, anything cool, I think it's a good opportunity to share.
Trick. Using AI. No, actually, one thing, I was working this year with people from different regions, different places in the world, like this team of Oink. So we have people from Barcelona, one from Sweden, one from Colombia. We have all over the world, and I think collaboration is key. So one thing that was very nice for me is to be super open-minded to people with different mentalities. Sometimes, somehow, it also gets reflected within the way the project moves. And when you give room and you give space to people, you discover wonderful things. So I think this is one thing that, thinking about this last year, this is one thing that comes up on my mind. It's not super technical, but it's great, I guess, for a project.
Okay, awesome. Thank you so much. And thank you everyone you that you onboarded and participated in this lecture. And thank you, Yogev. And yeah, see you next time. And I'll take this opportunity to say on Thursday, we're hosting Yuda Lindel with a collaboration with Coinbase as well. So we really wait to see you there as well. And thank you so much. Bye for now, everyone.